No, because we used IID back then, right? So we just used a simple IID model, right? So there are two ways to go about this. The first way is you first build a model from data and then encode using that model. This is the thing you did in homework. The other way, which we'll look at more this lecture, is adaptive, where you build the model from the data as you see the data, right? So as you see the data, you keep on building a model. I think this is the first time we are doing something like this. Let me show a block diagram before we look at the pros and cons of these two approaches. So again, past context, you have a model, but now the model is like not fixed. At every step, the model gives you the probability for the next symbol, you encode the next symbol, and then you update the model. And then you encode, yeah. So basically, as the model sees more and more data, it keeps on updating its state. It keeps on updating its own model, basically. The model keeps updating, it keeps training. We will do like a example of this. But for now, can anybody tell me how would you decode in this setting? Is decoding even possible with this sort of thing? What would the decoder need to do? This is adaptive. You are updating the model at every step based on all the data you have seen in the past.
Since the decoder is decoding one symbol at a time, it just needs to update its model accordingly for each symbol it sees. So in that way, it keeps it like basically is the same state in the model as the encoder did.
Yep. So the answer is decoder will decode a symbol, it will update. So we can like write it down as like a sequence of operations, right? So you take the decoder, so it will first decode U1, then it will update model. It will need to update the model in exactly the same way the encoder did. At any time if the models diverge, everything is lost. Decode U2, then you again update model. Right, so it basically does exactly what the encoder does, right? They go in sync. And this is very, very crucial. The encoder and decoder needs to share the same state at every step. If at any step the arithmetic coder sees different distributions, it will just break down. Like at any step, if it breaks down, then all the other steps are gone. This is fine for like simple models, but when you like try to do stuff with neural networks and so on, where like all these libraries have all sort of randomness, things just get very bad. It's very hard, like because when you're working with like machine learning applications, right? For ChatGPT, it's not important for a given input to always produce the same output. But for a compression model, it's very important that given a certain input, it should always give you the same probabilities, right? There can't be any like GPU level randomization. There can't be any like floating point stuff. So it's hard. Like people have to write their own libraries if they want to do compression with neural nets, basically. Like even if you write something, then it works on one GPU. So you compress a file on one GPU, you decode it on another GPU, and that breaks. So yes, very crucial. This one is also very important, right? During compression, right, you have the entire input, but you shouldn't get too eager. Don't like straight away update the model with UI before you encode UI. Always think of the decoder, right? It's always important to think of the decoder. Whenever each step you think of the decoder, what does the decoder know at this point, right? So let's say the encoder does this. It first updates model with U1 and then it encodes U1. What will happen now? Can the decoder still work? Right, I hear no, right, clearly, because decoder doesn't have U1, right? Encoder has the entire thing, encoder can do whatever, but the decoder can't start. So this is wrong, bad, okay. So it just need to be careful. This comes up in lossy compression also. There are some like these adaptive type schemes, just careful. Last thing is like never provide zero probability to any symbol, because if your model says that this symbol will never occur, and then it actually occurs, then log of 1 over 0 is like infinity. So your arithmetic coder will just break basically. So every symbol should, however small it might be, but it should always have a non-zero probability, right? Even if you think that a Q after a Q will never happen in English, provided like some small probability, never provided exactly zero probability. Okay, any questions? Right. So just like a pros and cons list, 2 paths. So one is that we learn model from entire data, right? So you look at the entire data. So maybe you get a better model at the end of the day, and you can parallelize the entire process more, because adaptive is sort of sequential. You're going through the data one by one. In the 2 paths, there are ways to parallelize it. However, you need to store the model in the compressed file. So that's not ideal. You need 2 passes over the data. This is like often a breaking thing in many applications where you can't just hoard data. You have to keep compressing the data as it comes in. You can't keep the entire data in memory. So this is usually a problem. And if your data has like statistics that change over time, right? Like if you have a file which is like start with a novel and then it suddenly turns into a code or something, then the model you learn will be a mixture of the 2 models and it won't do as well. Whereas adaptive might work like even in this case. So adaptive, the nice thing is you don't need to store the model. It is good for streaming. You can compress as it goes. One bad thing is that like initially the model is very bad. You don't know anything. You don't assume anything about the world. So initially you might get like slightly bad compression, but it works well in practice. So we'll look at one example of adaptive shortly. Any questions on adaptive arithmetic coding? Otherwise, I think we'll go to the example in a few slides. Okay. So just like sort of wrapping this up, this relation between compression and prediction that we have been seeing. So if you have done any machine learning class, like either neural networks or without neural networks or AI or whatever, you might have seen this cross entropy loss, also called log loss, for prediction. Right, so for prediction, your task is like you have a bunch of classes and then you're trying to predict which like you're given an image of something and you want to tell whether it's a cat or a dog or a cow. And most of the predictors, what they actually give you is a probability. So they give that 90% cat, 10% dog, 10% cow, let's say, right? And then you evaluate the model according to this loss function where you say that like, so if like this is a cat, right? And the model gives you like cat is 90%, dog is 5, cow is 5. Then the loss you get is like log 1 over 0.9, the probability of being a cat according to the model, right? So this forces the model to give higher probability to the correct symbol and lower probability to the not correct image and not correct label, right? But this exactly matches the thing we were just doing, right? So actually prediction and compression are exactly the same problem. Not much more to say. Like you can see the loss function is the same. Like it's literally the same loss function. The cost in arithmetic coding of encoding a thing is exactly the same as the prediction loss that we always use in ML. So what this tells you that if you have a good predictor in the ML sense, then it's a good compressor. And compression is all about having a good model for the data. If you have a good model for the data, then you automatically have a good compressor. You don't need to do anything special, right? Many compressors don't actually model the data. Like we'll see the LZ77, the one we'll see, it doesn't like actually model the data, but the compressors we see today will actually model the data. So it need not be explicit, but inherently there is a modeling going on. And final thing, this is sort of out of scope. We won't go into the details, but we are just doing arithmetic coding, right? But in many cases, you can use RANS with some tricks. And people are slowly like trying to use RANS in a lot of these applications. There are some issues, but some of them can be worked out. There is the opposite angle also. Not only does every predictor give you a compressor? Actually, every compressor gives you a predictor. This is a bit trickier, but it is true. And here the idea is, so if you have a compressor, encodes x1 through xn in L bits, then the predictor that the compressor gives you is basically given by this thing. So basically, each compressor is a predictor, each predictor is a compressor internally. It's like, you remember in the prediction thing, you have log 1 by p. So it's just like you do the formula, right? Log 1 over p. So p is equal to 2 to the minus L. So from any compressor, you can actually create a probability model for your data. This is slightly advanced. We will not worry too much about it, but it is a thing. There is a paper I will tell you about, very recent paper, that actually took like gzip, which is a very common compressor, and turned it into a predictor. Didn't do very well, but you can do these things. Okay. So prediction models used for compression. Okay, so now we'll look at a few specific prediction models, do some like examples, and then do a few very fun experiments. Okay. So this is kth order adaptive arithmetic coding. So what you are trying to do here is you are trying to learn a kth order model for your data as you go through the data. Let's just read the last line. Don't look at the rest of it. I think you will understand from the example the rest of it. So if you have seen BA/NA in the past several times, and 90% of the times you saw it being followed by a N, so for a banana, for example, and 10% of the time you saw it followed by a L, that is your model basically. The next time you see BA/NA, you would say that maybe it's a N with probability 90% and L with a probability 10%, right? So just you use the past to predict the future, as simple as that. So let's do an example, which should make it clear. So we are doing first order adaptive arithmetic coding. So this means you need to actually keep second order statistics. You will understand why. So initially and this is your data you are going to encode 101011. So initially you assume everything is like 1. You have some frequencies or counts. So you assume that this is to avoid the problem we talked about before, right? When you don't want anything to have a 0 probability. So you assume that you've already seen a 0, 0, you have seen a 0, 1, you have seen a 1, 0, you have seen a 1, 1. You have seen all 4 one time in the past. Okay. So the first symbol you see is 1, and here you don't have a past. So what we'll do is we'll add a 0 at the front, just as a fake 0. Okay, padding. Now, looking at these counts, what is the probability that a 0 is followed by a 1? Like if your past is 0, what is the probability that the next one is a 1? How many think it's 1? The probability that a 0 is followed by a 1. How many think it's 1/3? Half? Very few votes for half. Okay, half is the correct answer, right? So not very tricky, right? So basically what we are doing is this is the equation. The probability that a 0 is followed by a 1 is you take all the cases where you say 0, 1 in the numerator, and you take all the cases where you see 0, 0 plus 0, 1 in the denominator, that sort of thing, right? So basically like what this is saying is you saw like 0, 1, n0, 1, like let's say you saw this like 9 times, and you saw like 0, 0, 1 time, then you would say that the probability that 0 will be followed by 1 is 9/10, right? So just like 9 out of 10 times you are seeing that a 0 will be followed by 1, as simple as that. Okay. And now you have seen a 0, 1, so you update your count. You update your count of 0, 1 by 1. So you do 1 plus 1 equal to 2. Okay, are we happy with this? And then we'll do the next, but let me pause for a sec. Okay. Right, and now we do the next symbol. So next symbol is 0. So now you need to, and the previous symbol is 1, right? So next symbol is 0, previous symbol is 1. So you do like probability of 0 given 1 based on this model. Just follow the math. Again you get a half, again you update the model. Okay, let me do the next one, which is more interesting. So now you have your previous symbol is a 0 and next symbol is a 1, right? But remember that due to the padding, you have already seen a 0, 1. So now your model should sort of lean towards, oh, maybe a 0 is more often followed by 1 and less often followed by a 0. And yeah, that's what it does. It gives you a 2/3 probability instead of a half probability, which it gave you last time, right? So as you see more and more data, it will like learn the statistics of your data and start giving you like predictions which are consistent with your data. And at every step, you keep updating your model. I think you will have a chance to play with this, actually make your own model in one of the homework questions. So that should be exciting. Right, so the idea is that over time you learn the empirical distribution of the data as you see the more and more data, right? And initially you start off with a uniform distribution in the example we did. But if you know something about the data, you can use that to initialize your counts. Make sure encoder and decoder both know, and also make sure nothing is 0, basically, like never make anything 0, because if you make anything 0, then everything breaks. And one final thing, for that question from homework 1 that you all did, you could have used this with k equal to 0. You could set k equal to 0. So what you could do is, like let's say you have seen 1 0 1 1 0 0 0 1 1 1, and the next symbol is a 0, which is what you want to encode. So in the past you have seen 1 2 3 4 5 6, so 6 ones and 4 zeros. So you could just make a model where this is 4 by 10. And then the next symbol, let's say that's also a 0. Can anybody tell me what will be the predicted probability of the next symbol if this guy had a probability of 4 over 10? 5 over 11 I hear. Yes, I think. Because the last symbol will increase the count of zeros and increase the count of ones, right? So just the counts, nothing special. Okay. So you can implement it. We implemented it. We took the Hound of Baskerville and we ran it. Okay. So zeroth order is basically assuming an IID model. First order assumes a first order model, second order, third order. We also ran 2 like standard compressors as benchmarks, gzip and bzip2. Okay, so somebody tell me, why does it improve when you go from 0 to second order? Let's say your input was actually IID. There was no dependence. Do you expect it to improve if you use a larger context? No, right? So clearly there is some relation, and you know that English has, right? English, if you know the past 2 symbols, you can predict the next symbol better. So therefore it will improve as you increase the order. Now can somebody tell me, why did it not get better for third order? Why did it actually get worse? Recall that the file has like a certain size. It's like a few hundred kilobytes. It's not infinite. In a smallish file, do you expect to see like a sequence like ABCD or something? Like do you expect to see a sequence of length 4 many times in a very short file, right? If you have a small amount of data, you won't even get any counts. That is the issue. You start with your initial uniform model, And you never get enough counts to like make that model into something useful because you have such a small, because if you think about it, right, the count array basically, right? So for first order, you need like pairs, you need like xi comma xi plus 1, and then for second order you need like xi plus 1, xi plus 2, you need like 3 at a time, and so on. So this grows like exponentially in the order basically. So if your alphabet size is x and so this is your order, then this is the number of counts you need to maintain. So if you have a very small amount of data, your counts will be very sparse. Most of them will be 0. You won't see most of the patterns. And since you don't see most of the patterns, you get like a very poor predictor and it doesn't do well. So if you don't have a lot of data, then higher order models start breaking. Because we have a very silly model, right? It just like looks at the past. And so for example, like just as an example, right? Like let's say you see like THIN. And then you're trying to predict the next symbol. But if you have never seen THIN in the past, you have no model for it. So it won't do anything useful, right? So unless you have a large enough text where you see that thing many, many times, it won't learn anything. So that's why it got worse here, okay? And we see that gzip and bzip2 actually beat these models, and we'll talk about them in next lecture. So we talked already about Wise order 3 doing worse than order 2. So there are limitations. Kth order becomes slow. The memory grows exponentially in k. The counts become very sparse for large k. As you increase k, the counts just, you don't have many counts, and it leads to worse performance. And this is sort of like a interesting point where just an example, right? Let's say you have THI and capital THI, right? If you had a smart model, it would know that, okay, these two are just the capitalization is different, but there is some relation. If you have seen like THIS many, many times, even for uppercase T, it should predict that this is, maybe it's the S, right? But if you have that silly adaptive arithmetic coder kth order model, that doesn't know. Everything looks different to it. It has no like understanding of English. It has no understanding of anything. And it just treats any two contexts, any two past sequence as just distinct. Just stores two separate counts for all of them. So doesn't do as well. We can improve them. Okay. I said a lot of bad things. It's not the end of, like people use this. They are used in certain specific scenarios, but they're not the best models. But they're simple models, and you can try them. Okay, now I did another thing. I said, okay, I did the adaptive thing, right? But if I did a two-pass thing, I can compute the conditional entropy from the data. And now I see, oh, for zeroth order, they are very close. For first order, there is a small gap. For third order, the empirical conditional entropy keeps improving. So if I did a two-pass approach, it seems like I could do a really, really good job. Like in the Huffman case, you did a two-pass approach, if you remember. Would you do a good job? What do you think? So if you're doing a third order model, okay, so let's say in your entire text, you see THI only once, right? And it was like followed by S, let's say, in your entire text. So how many bits do you spend to encode S? If you have seen it only once and the one time it was followed by S, you basically, can somebody tell me? None, right? You spend 0 bits. You spend 0 bits to encode the next symbol because you only saw it once, so the probability distribution is deterministic. But how does the decoder know? Yes. Basically what you are doing is the model basically now starts storing the data. As you increase k, what happens is, think of the extreme, think of the very extreme. Like let's say you have a text of length 1000, and if you take a 1000th order model, then there is only one 1000 length sequence in the entire input. It has probability 1. You encode it in 0 bits. You don't need any bits to encode it, right? So this is just like a thought experiment where you take, so let's say your input is like 1000 bits, okay, and 1000 symbols, and you take like a 1000 order model. So the probability of the input is 1, probability of everything else is 0, right? You just store your entire data in your model and you say, oh, I encoded it in 0 bits because my model is perfect at predicting my particular data, right? Like you take a Sherlock Holmes novel, your model contains the entire Sherlock Holmes novel, right? And you encode it in 0 bits. You don't need to send anything. The decoder knows it's a Sherlock Holmes novel. So this is silly. This is not how we should do it, right? So, oh no, okay. So as the order increases, basically knowing the empirical distribution basically becomes storing the data in the model. So you're not doing anything smart at that point. You're just storing your data in the model. Right? Recall that the model size is like exponential in the order, right? So as the order becomes bigger, the model overwhelms everything. And therefore you need to account for the cost of storing the model. And this is another reason where adaptive models are often preferred, because just you don't need 2 passes and so on. There is this principle, we won't talk too much about it, but like I think this will convey what I was trying to say. Like as you make your model more and more complex, your compressed size will reduce because your model will at some point start learning your data. But the model size will increase exponentially. And so the total size is what you care about, the size of the model plus the size of the data. And there is some point where it's like optimal, like in this figure it's here. At some intermediate model complexity, you will get like the best overall result. This principle is called like minimum description length by Rissanen, who is like one of the people who did a lot of interesting theory in compression. And he is one of the creators of arithmetic coding actually. So good work. Okay, any questions so far? We will, I don't think we'll get to LZ today, but we'll do some fun things. Okay, any questions? So we saw adaptive kth order modeling. We saw what happens if you do a 2-pass and you keep increasing the order. And we saw that the kth order thing has some issues, right? The counts become sparse, it gets harder. So this is something we won't go in too much detail, but it's a great project idea basically if you want to do any of these. So the kth order adaptive is implemented in the library. Solving the sparse count problem. There are a couple of ways where you can actually partially solve that issue. There's something called PPM, something called CTW. And what they do is that maybe I've not seen THI before, but maybe I've seen HI before, or maybe I've seen just I before. So you mix a bunch of things and you try to try to compensate for the fact that maybe you have not seen longer context, but you have at least seen shorter context. So at least use those. Like don't throw away information that you already got. Again, not going into details, sadly. Okay, then there are some advanced prediction models. I have links here. I will talk over a couple of them. And really this book is like, if you want to really understand these and implement these, this is like a online textbook by Matt Mahoney, who has done like a lot of interesting work on like heavy duty compressors in particular. Yeah. So all of these are typically the most powerful compressors around, but very slow for many practical applications. Okay. So just very quickly, like 2 of these advanced models, some of them are neural net based, where what they do is, So it basically like you have given the past symbols, you have a neural network predictor, and then that goes into arithmetic encoder, right? And similarly for the decoder, right? So we just changed our adaptive thing to a neural network predictor, which will again give you the probabilities. And you can do a 2-pass approach, or you can do an adaptive approach. So you can keep updating your neural net. Just like you had a count thing, you can do a neural net thing, basically is what we are saying. For CMIX, the other one I mentioned, this is very advanced ideas where what they do is they have like thousands of different models. You predict based on the last bit, you predict on last 2 bits, last 3 bits, previous word, first letter of previous word, last letter of previous word, whether this word is the first word in the sentence or the second word, just a bunch of different contexts. And then they have a neural net that mixes all those into like a single probability. There is a talk, I know you won't appreciate from what I just said, but there is a talk from last year's IT forum where the author of this CMIX came to talk, and this is a slide that Pulkit created at some point, which just shows over time how has compression for text improved. And this is gzip, bzip2, 7zip, right? And here we show like if you assume that the characters are uniform, it's very bad. Bits per character is like more than 4. If you assume like word level some modeling, then it gets lower. And last time we saw some estimate by Shannon where he did some human experiment to try to estimate the entropy rate of English. And we have, as you see on the far right side, we have actually beaten that now. With these CMIX and NNCP models, we are doing better than Shannon's estimate of the entropy rate. So I've really come very far in compressing text. Even though text in many cases is not something, like there isn't a lot of text, like all the text created by humans is like a few terabytes or something. It's far from like the biggest data source, but I think we are just curious to compress text as well as possible. And any questions? Okay, so if you didn't listen to anything, please listen to this because I'm very excited about this. Now, remember that good prediction equal to good compression, right? So today the most powerful predictors are these LLM models, right? So this is new material. We didn't have this last year. So now forget about that MDL setting that we have been working with where like we said that the model is very big, that's bad. No, now we don't worry about storing the model. Just get the best compression. Bring your biggest model. Okay, so throw your most powerful predictor at a problem. Gigabytes, hundreds of gigabytes of model, that's fine. So in a normal setting like this is not useful because where would you store the model? And obviously if you store that model with the file, that doesn't make sense. Can anybody think of any domain or any sort of setting where you can, it's fine to have a very big model as a predictor? So what is the issue with having a very big model as the predictor? We said we need to store the model as part of the compressed file. But do we? Maybe we don't, right? Maybe there is a world where everybody has GPT-4 on their mobile or on their laptop or whatever, right? And then everybody assumes that everybody else has that huge model on their machine and everybody uses that single model to compress things and send it to each other. So there are settings, right? So if you have a large amount of data of the same type basically, and you can afford to deploy the model everywhere, which might become a reality. There are two other reasons to do this. One is that we want to understand the limits of compression. How good can your text prediction become? And other is just to like have fun in a compression class. So for me, the third reason really. Right, so basic model is simple, right? Predictor gives you compressor, log loss. So basically, if you think of LLMs are trained as predictors, and their loss function is the cross entropy loss or 2 power the cross entropy loss. So in effect, they are becoming compressors, right? They are actually compressors. And I took this recent work by the same person who made NNCP, who made this text compression using large language models, where you can like download any model and then use that to compress your favorite text. And I did like a couple of things. So I took a 2023 novel, and I took second order arithmetic coding. I took bzip2, and I took two models, and I took like different context lengths. So context length is like how much of the past number of tokens you see. So you see that if your context length is not very large, if you just look at the last 16 tokens, it does better than bzip2, but not like very impressive. And the medium size model, which is in darker shade of blue, does slightly better than the small model. But it really starts to shine when you take a long context. That's the thing with these large language models, right? They can look at a very big past history and make a very good prediction for the next token based on that. We saw it in the earlier part of the class, if you remember, where the more context you give, the better the prediction becomes. So once you give it like a long enough context, it starts getting to the point where it's like below the Shannon bound, very close to CMIX and NNCP. So it's basically the optimal. And this is a very small model. It's a 430 million parameter model, whereas the GPTs are like tens of billions or more. Any question on this? Like, do you generally understand the idea? Bigger model, better compression, or I guess better model, better compression, more context, better compression, not counting the model size. Okay, now I did this. Instead of like having this English novel released in 2023, I took like Pali is an ancient Indian language. I took this text which was transcribed in Roman script, and I compressed it with again all of these guys. Now you see like actually the models are not able to beat bzip2 or even gzip. Can anybody tell me why? Pali is like Sanskrit, if you've heard of that.
Presumably these LLMs are trained on like, they're like a universal model, so they're not really trained for the specific thing, but easy presumably will have the model based on the specific distribution. Yeah. So the idea is that these LLM models, oftentimes the training data set is English, right? Especially for these smaller models, the training data set is limited to like a certain corpus. I didn't try like GPT-4 because I don't have it. It would just take too long, I think, to do. But maybe that will do better. But yes. So gzip, bzip2, second order arithmetic coding, they don't make any assumption about the data. They will work for any type of data. So that is the beauty there, that they are like in a sense, gzip and bzip2 are like universal in a sense. They don't care about your data. They just, for any type of data you give, they will, if it's a big enough sample of data, they will learn the distribution from the data and do a good job. These LLM models, they assume that the data is of a certain distribution, and if your data is not from that, then they do worse. Then Kedar did some experiments where he took an even bigger model, a Llama 13 billion parameter model, on a short story, again released in 2023. He tried different context lengths and he got like different bits per byte, compressed bits per character. Higher context length, better. Nothing changed until now. I guess you can see the number 0.874 is a bit better than the ones we got here. Presumably because the model is stronger. Llama is like a much stronger model than these ones. Then we tried something else. We tried the same model on a Sherlock Holmes novel. And you see this number, 0.2. So earlier we were always talking like around 1 bits per byte. Suddenly you are getting like 0.2 bits, 5x more compressed. So this means either two things. One, either like Sherlock Holmes or like Arthur Conan Doyle's English was much simpler than these modern short story novels, or something else is going on. And any suggestions? Why is the compression ratio so good for this new sorry, for this Sherlock Holmes thing on the Llama model? Do you know how the Llama model was created? What did they do to create the model? Nobody? Any guesses? Yeah, they used old books, right? Like among other things, they looked at Wikipedia. So Llama was trained on a bunch of things, including, I assume the Sherlock Holmes thing was part of the training data set. And therefore,
I guess it memorized some of it, and it's just doing like an exceptional job at compressing the Sherlock Holmes novel. So one needs to be careful, right, when evaluating. That's why like all of the times we were using this 2023 thing, which we assumed was not part of the very recently released things. Okay, so last slide. Okay, so LLM based compression, remarkable results. Can be it's really like we are pushing it to the limit, right? So for a compression perspective, it's just useful to know, even if these are not going to like be the most practical ones. We need to be careful about a couple things we saw. One is that the model and the data, if they are not aligned, then you get not so good results. And when you're evaluating things, just make sure to not use something from the training data. Otherwise, your results might be misleading. Right now, they're very slow and very compute intensive. But actually, like the smaller model that we did, that was like reasonably fast on a GPU. So it is possible that for some applications, these might actually be used in the future.
Can I add a point with you?
Yep.
Yeah, so, but something to notice here is why LLMs even work. Irrespective of like how in machine learning you want to be careful about overfitting and avoid. For the compression sake, if you come up with a model which is really overfitted on whatever you are compressing on, and the model is shared, it's actually a good thing. It's not a bad thing. You might want to overfit and share that model everywhere if you can on the specific data sets you would like to work to. Why in practice it becomes a hard thing to do, because at that point you need bigger and bigger models, you need higher and higher latencies. But for compression's sake, it might not be bad to overfit and pre-share that model on both sides if you can. That's the context in which this LLM-based compression is working.
Yeah. So Pulkit makes a good point where for compression, it's not necessarily a bad thing. Like if you actually want to send a Sherlock Holmes novel to another person, good compression is good, right? It doesn't hurt you. Obviously, like if your model is going to learn everything, then the model gets very big. So there are issues there. But I guess that's why they are so good, because they know everything from the past and still they are able to generalize very well. Even on the latest data sets, they are like state of the art. Okay. So a couple resources. One is this TSZip. So the thing that this one, Kedar ran these experiments. It's a very nice notebook with you will see how we did the thing where we tried to predict the next, like the thing we did at the start, right? Predicting the next token. That's also in this notebook, and how to do compression. However, this one, if you like actually compress it. Oh yeah, one thing, just quick note is that when you're like trying to evaluate these things, you know that arithmetic coding will give you this log 1 by p thing, right? So oftentimes we don't even do arithmetic coding. We just calculate summation of log 1 by p, and we assume that's what arithmetic coding is going to give us, because it has like a 2-byte overhead or something, 2-bit overhead. So that's just like a useful thing to know in practice. Like you don't actually need to do arithmetic coding to know how well your compressor or predictor is performing. Just compute the log loss. And DeepMind had a recent, Google, they had a recent paper called Language Modeling is Compression. Very nice title. I think it's an interesting read. Now I think with what you have learned, and if you know a little bit about LLMs, you will be able to understand that entire paper. So I encourage you to take a look. Okay, so next lecture we will do LZ77, and depending on time, and with like some practical aspects about lossless compression. Thank you.